Physics is the natural science that studies matter, energy, and their interactions. It encompasses a wide range of phenomena, from the smallest subatomic particles to the largest structures in the universe, and it seeks to understand the fundamental laws that govern the behavior of all physical systems. Physicists use mathematical models, experimental data, and theoretical reasoning to develop our understanding of the natural world, and their discoveries have led to countless technological innovations that have transformed society. Some of the major areas of physics include classical mechanics, electromagnetism, thermodynamics, quantum mechanics, relativity, astrophysics, and cosmology. What is a physical quantity? Physical quantity is a property or attribute of a physical system that can be quantified, meaning it can be expressed in terms of numerical values and units of measurement. Examples of physical quantities include mass, length, time, temperature, electric charge, and velocity. Physical quantities can be classified into two types, scalar and vector quantities. Scalar quantities have only magnitude, which means they are represented by a single numerical value and a unit of measurement. Examples of scalar quantities include mass, temperature, and time. On the other hand, vector quantities have both magnitude and direction, which means they are represented by a numerical value, a unit of measurement, and a direction. Examples of vector quantities include displacement, velocity, and force. Physical quantities can be measured using various instruments, such as rulers, thermometers, scales, and oscilloscopes. Accurate measurements of physical quantities are essential for understanding the behavior of physical systems and for developing scientific theories that can predict and explain the behavior of natural phenomena. Physical quantities are expressed in the International System of Units, SI. M/S represents meters per second, which is the unit of measurement for speed or velocity. It is equivalent to ms-1, which means meters per second raised to the power of -1. M/s-2 represents meters per second squared, which is the unit of measurement for acceleration. It is equivalent to ms-2, which means meters per second squared raised to the power of -1. kg/m-3 represents kilograms per cubic meter, which is the unit of measurement for density. It is equivalent to kgm-3, which means kilograms per cubic meter raised to the power of -1. Here are some examples of physical quantities, their units, the base quantities they are derived from, and their corresponding SI units. Length, meter, m, derived from the base quantity of distance, measured by a ruler or other distance measuring instruments. Mass, kilogram, kg, derived from the base quantity of mass, measured by a balance or scale. Time, second, s, derived from the base quantity of time, measured by a clock or stopwatch. Electric current, ampere, A, derived from the base quantity of electric current, measured by an ammeter. Temperature, Kelvin, K, derived from the base quantity of temperature, measured by a thermometer. Amount of substance, mole, derived from the base quantity of amount of substance, measured by counting the number of particles in a sample. Luminous intensity, candela, CD, derived from the base quantity of luminous intensity, measured by a photometer. The SI units, or International System of Units, is a system of measurement based on the 7 base quantities listed above. It is the most widely used system of measurement in science, engineering, and everyday life. It provides a consistent and coherent framework for measuring physical quantities, and it ensures that measurements made by different people in different places are comparable and reliable. Here are some examples of submultiples and multiples of SI units, their corresponding prefixes, abbreviations, and powers of 10. Length. Kilometer, km 10 cubed meters. Centimeter, cm 10 carat, -2 meters. Millimeter, mm 10 carat, -3 meters. Micrometer, M10 carat, -6 meters. Nanometer, NM10 carat, -9 meters. Picometer, PM10 carat, -12 meters. Mass. Kilogram, kg 10 cubed grams. Milligram, mg 10 carat, -3 grams. Microgram, g 10 carat, -6 grams. Nanogram, ing 10 carat, -9 grams. Time. Millisecond, ms 10 carat, -3 seconds. Microsecond, s 10 carat, -6 seconds. Nanosecond, ns 10 carat, -9 seconds. Electric current. Milliampere, ma 10 carat, -3 amperes. Microampere, a 10 carat, -6 amperes. Temperature. Celsius, degree C not applicable, no prefix is used for Celsius temperature. Kelvin, K not applicable, no prefix is used for Kelvin temperature. Amount of substance. Millimole, mole 10 carat, -3 moles. Micromole, mole 10 carat, -6 moles. Luminous intensity. Millicandela, MCD 10 carat, -3 candelas. The prefixes used to indicate submultiples and multiples of SI units are based on the powers of 10. Each prefix represents a specific power of 10, and they are abbreviated with a single letter. For example, K represents 10 cubed, M represents 10 carat, -3, microsine represents 10 carat, -6, and so on. The abbreviation for each unit is formed by combining the prefix with the abbreviation of the base unit. For example, km represents kilometers, mg represents milligrams, and s represents microseconds. Standard form. Standard form, also known as scientific notation, is a way of expressing very large or very small numbers using powers of 10. In standard form, a number is expressed as a coefficient multiplied by 10 raised to a certain power, where the coefficient is a number between 1 and 10, and the power is an integer. For example, the number 3,450,000 can be written in standard form as 3.45 times 10 to the power of 6, where 3.45 is the coefficient and 6 is the power of 10. This means that the number is equal to 3.45 multiplied by 10 raised to the power of 6, or 3.45 million. Similarly, the number 0.00000072 can be written in standard form as 7.2x 10 carat, -6, where 7.2 is the coefficient and -6 is the power of 10. This means that the number is equal to 7.2 multiplied by 10 raised to the power of -6, or 0.00000072. Standard form is commonly used in science, engineering, and mathematics to represent very large or very small numbers in a concise and convenient way. It also makes it easier to perform calculations with these numbers, since it allows us to manipulate the coefficients and powers separately. Significant figures. Significant figures, also known as significant digits, are the digits in a number that carry meaning or contribute to its accuracy. In other words, significant figures are the numbers that we know with certainty, plus one additional digit that is estimated or uncertain. The rules for determining significant figures are as follows. All non-zero digits are significant. For example, the number 123 has 3 significant figures. Zeros between non-zero digits are significant. For example, the number 506 has 3 significant figures. Leading zeros to the left of the first non-zero digit, are not significant. For example, the number 0.004 has 1 significant figure. trailing zeros to the right of the last non-zero digit, are significant only if they are to the right of the decimal point or if they are indicated by a bar over the top of the zero. For example, the number 50.0 has 3 significant figures, and the number 5000 has 4 significant figures if a bar is placed over the last zero, 5000. In numbers that contain both a decimal point and a bar over the top of a zero, the number of significant figures is determined by the number of digits between the first non-zero digit and the last significant digit. For example, the number 0.05000 has 3 significant figures if a bar is placed over the last zero, 0.05000. Significant figures are important in scientific measurements and calculations because they indicate the precision and accuracy of the data. When performing calculations with measured values, the number of significant figures in the final answer should be no greater than the number of significant figures in the least precise value used in the calculation. This helps to avoid giving the impression of greater accuracy than is actually warranted by the data. A pendulum is a simple mechanical device that consists of a weight, called the bob, attached to a fixed point by a rod or string. When the bob is displaced from its resting position and released, it swings back and forth in a regular pattern called an oscillation. Here are some important definitions related to a pendulum. Amplitude, the maximum displacement of the bob from its resting position during an oscillation. Period, the time it takes for the bob to complete one full oscillation. It is usually denoted by the symbol T. Frequency, the number of oscillations per unit time. It is the reciprocal of the period and is usually denoted by the symbol F. Length, the distance from the fixed point to the center of mass of the bob. It is usually denoted by the symbol L. Displacement, the distance between the resting position of the bob and its position at any given time during an oscillation. It is usually denoted by the symbol X. The motion of a simple pendulum can be described using the following formulas. Period. The period of a simple pendulum is given by the formula T equals 2 pi square root L/g, where L is the length of the pendulum and g is the acceleration due to gravity. Frequency. The frequency of a simple pendulum is given by the formula F equals 1/t equals 1/2 pi square root g/L. Amplitude. The amplitude of a simple pendulum is the maximum displacement of the bob from its resting position. The amplitude of a pendulum does not affect its period, but it does affect the maximum speed of the bob during its oscillation. Displacement time graphs. A displacement time graph, also known as a position time graph, is a graph that shows the displacement of an object over time. The displacement is usually plotted on the y-axis, vertical axis, while the time is plotted on the x-axis, horizontal axis. The slope of a displacement time graph at any given point represents the velocity of the object at that point. If the slope is positive, the object is moving in the positive direction, while a negative slope indicates motion in the negative direction. A horizontal line on a displacement time graph indicates that the object is not moving, i.e., its displacement is not changing over time, while a vertical line indicates an instantaneous change in displacement, i.e., the object has moved a certain distance in zero time. The area under the curve of a displacement time graph represents the total displacement of the object over a given time interval. If the area is positive, the object has moved in the positive direction, while a negative area indicates motion in the negative direction. Displacement time graphs can also be used to analyze the motion of an object and to determine its acceleration. The acceleration of an object is represented by the slope of the velocity time graph, which can be obtained by calculating the slope of the displacement time graph at two different points and dividing the difference by the time interval between them. Overall, displacement time graphs provide a visual representation of an object's motion over time and can help to identify patterns and trends in its behavior. Gradient of a graph. The gradient of a graph is a measure of its slope or steepness at a given point. Mathematically, the gradient of a graph is defined as the rate of change of the y-coordinate with respect to the x-coordinate at a particular point on the graph. To find the gradient of a straight-line graph, we can use the formula. Gradient equals change in y-coordinate / change in x-coordinate. This means that the gradient of a straight line is equal to the change in its y-coordinate divided by the change in its x-coordinate. The gradient can be positive, negative, or zero, depending on the direction and steepness of the line. For example, consider a straight line that passes through 2 points x1, y1, and x2, y2 on a graph. The gradient of the line can be calculated using the following formula. Gradient equals y2 y1 / x2 x1. This formula gives us the change in the y-coordinate divided by the change in the x-coordinate between the 2 points, which represents the slope of the line. The gradient of a curve is not as straightforward to calculate, as the slope of the curve varies at different points. However, the gradient at a specific point on a curve can be approximated by drawing a tangent line to the curve at that point and calculating the gradient of the tangent line using the formula for the gradient of a straight line. The tangent line represents the instantaneous rate of change of the curve at that point, which is also known as the derivative of the curve. Hooke's law is a principle in physics that describes the relationship between the extension or compression of a spring and the force applied to it. The law states that the force required to extend or compress a spring by a certain distance is directly proportional to that distance. The equation for Hooke's law is expressed as F equals kx, where F is the force applied to the spring, x is the extension or compression of the spring, and k is the spring constant, which is a measure of the stiffness of the spring. Important concepts related to Hooke's law include elastic deformation. This is the temporary deformation of a spring when a force is applied to it, but the spring returns to its original shape when the force is removed. Plastic deformation. This is the permanent deformation of a spring when a force is applied to it, and the spring does not return to its original shape when the force is removed. Limit of proportionality. This is the point beyond which Hooke's law no longer applies and the spring becomes permanently deformed. It is the maximum force that can be applied to the spring without causing permanent deformation. Spring constant. This is a measure of the stiffness of the spring and is defined as the force required to extend or compress the spring by a certain distance. In CXC Physics, Hooke's law is usually studied in the context of springs and elastic bands. It is important to understand the concepts listed above and to be able to apply the equation F equals kx to solve problems involving springs and elastic bands. This may involve calculating the spring constant, finding the extension or compression of the spring, or determining the force required to stretch or compress the spring by a certain distance. Density. Density is a physical property of matter that describes the amount of mass per unit volume of a substance. It is calculated by dividing the mass of an object by its volume. The formula for density is density equals mass/volume. The unit for density is typically expressed in grams per cubic centimeter, g/cm3, in the metric system. In other systems of measurement, it may be expressed in pounds per cubic inch, lb/in3, or kilograms per liter, kg/L. Some important concepts related to density include mass. This is the amount of matter that an object contains. It is typically measured in grams, g, or kilograms, kg. Volume. This is the amount of space that an object occupies. It is typically measured in cubic centimeters, cm3, cubic meters, m3, or liters, L. Density of water. Water is often used as a reference substance for density measurements, as it has a density of 1 g/cm3 at standard temperature and pressure, STP. Density and buoyancy. Density plays a key role in determining whether an object will float or sink in a fluid. An object with a density greater than that of the fluid will sink, while an object with a density less than that of the fluid will float. Changing density. The density of a substance can change with temperature and pressure. As temperature and pressure increase, the density of a substance usually decreases. Density is an important concept in many fields of science and engineering, including chemistry, physics, and materials science. The equations listed below are some of the most important kinematics equations that are commonly used in CXC physics. They relate to the motion of an object that is moving with a constant acceleration. V equals u plus at. This equation relates the final velocity, v, of an object to its initial velocity, u, acceleration, a, and time, t. It can be used to calculate the final velocity of an object that is moving with a constant acceleration. S equals ut plus 1/2 at caret 2. This equation relates the displacement, s, of an object to its initial velocity, u, acceleration, a, and time, t. It can be used to calculate the displacement of an object that is moving with a constant acceleration. V squared equals u squared plus 2 as. This equation relates the final velocity, v, of an object to its initial velocity, u, acceleration, a, and displacement, s. It can be used to calculate the final velocity of an object that is moving with a constant acceleration. S equals 1/2 u plus v, t. This equation relates the displacement, s, of an object to its initial velocity, u, final velocity, v, and time, t. It can be used to calculate the displacement of an object that is moving with a constant acceleration. Some key concepts related to kinematics equations include velocity. This is the rate of change of displacement with respect to time. It is usually measured in meters per second, m/s. Acceleration. This is the rate of change of velocity with respect to time. It is usually measured in meters per second squared, m/s caret 2. Displacement. This is the change in position of an object over a certain time interval. It is usually measured in meters, m. Time. This is the duration of a particular motion or event. It is usually measured in seconds, s. Scalar and vector quantities. Scalar quantities have only magnitude, while vector quantities have both magnitude and direction. Velocity, acceleration, and displacement are all vector quantities, while time is a scalar quantity. By understanding and applying these equations and concepts, students can analyze and solve problems related to the motion of objects with a constant acceleration. This is important for a variety of applications, from predicting the behavior of moving vehicles to designing and testing new technology. Freefall. Freefall is the motion of an object that is falling under the sole influence of gravity, with no other forces acting upon it. When an object is in freefall, it accelerates towards the ground at a constant rate known as the acceleration due to gravity. The acceleration due to gravity is denoted by the symbol g and is approximately 9.8 meters per second squared, m/s caret 2, near the surface of the Earth. This means that an object in freefall near the surface of the Earth will experience a constant acceleration of 9.8 m/s caret 2 towards the ground. Some important concepts related to freefall include terminal velocity. This is the maximum speed that an object can reach during freefall due to air resistance. As an object falls through the air, it experiences air resistance, which opposes its motion and causes it to slow down. When the air resistance is equal to the force of gravity, the object reaches its terminal velocity and falls at a constant speed. Acceleration. Freefall is a type of motion that is characterized by a constant acceleration due to gravity. This means that the speed of the object increases at a constant rate as it falls. Freefall is an important concept in physics, as it plays a role in many real-world applications, such as skydiving, bungee jumping, and parabolic flights. By understanding the principles of freefall and its associated equations, students can analyze and predict the motion of objects in freefall and better understand the behavior of objects in the world around us. Linear momentum, denoted by the symbol p, is a physical quantity that describes the motion of an object. It is defined as the product of an object's mass, m, and its velocity, v. Mathematically, this can be expressed as p equals m asterisk v. The SI unit of linear momentum is the kilogram meter per second, kg asterisk m/s. It is a vector quantity, meaning it has both magnitude and direction, and its direction is the same as the direction of the velocity vector. Another important concept related to linear momentum is the principle of conservation of momentum, which states that the total momentum of a system of objects remains constant if there are no external forces acting on the system. This can be expressed as sigma p underscore before equals sigma p underscore after, where sigma p underscore before is the total momentum of the system before a collision or interaction, and sigma p underscore after is the total momentum of the system after the collision or interaction. In the case of a two-body collision, the conservation of momentum can be expressed as m1u1 plus m2u2 equals m1v1 plus m2v2, where m1 and m2 are the masses of the two bodies, u1 and u2 are their initial velocities, and v1 and v2 are their final velocities after the collision. Linear momentum is an important concept in physics, as it is conserved in many types of interactions, including collisions and explosions. In physics, a collision occurs when two or more objects come into contact with each other and exchange energy and momentum. Collisions can be classified as either elastic or inelastic, depending on the amount of kinetic energy that is conserved during the interaction. Elastic collisions are those in which the total kinetic energy of the colliding objects is conserved. This means that the kinetic energy before the collision is equal to the kinetic energy after the collision. In an elastic collision, the colliding objects rebound off each other with no loss of kinetic energy. An example of an elastic collision is two billiard balls colliding with each other on a frictionless table. In this scenario, the total kinetic energy of the system is conserved, and the two balls rebound off each other with no loss of kinetic energy. Inelastic collisions, on the other hand, are those in which the total kinetic energy of the colliding objects is not conserved. In an inelastic collision, some of the kinetic energy is converted into other forms of energy, such as heat or sound. In an inelastic collision, the colliding objects may stick together or deform upon impact. An example of an inelastic collision is a car colliding with a wall. In this scenario, the kinetic energy of the car is not conserved, as some of the energy is transferred to the wall as heat and sound. The difference between elastic and inelastic collisions can be seen in the mathematical equations that describe them. In an elastic collision, both the momentum and kinetic energy of the system are conserved, while in an inelastic collision, only momentum is conserved. The study of elastic and inelastic collisions is important in many areas of physics and engineering, including vehicle safety, materials science, and ballistics. By understanding the principles of these types of collisions, students can better understand the behavior of objects in motion and predict the outcomes of collisions in the real world. Newton's laws of motion are three fundamental laws in physics that describe the behavior of objects in motion. They were first described by Sir Isaac Newton in his book Philosophiae Naturalis Principia Mathematica in 1687. These laws are the foundation of classical mechanics and are essential for understanding the motion of objects in the world around us. Here are the 3 laws. Newton's first law, the law of inertia. Newton's first law states that an object at rest will remain at rest, and an object in motion will remain in motion with a constant velocity, unless acted upon by an external force. This is also known as the law of inertia. In other words, an object will maintain its state of motion unless acted upon by a net external force. Newton's second law, the law of acceleration. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to its mass. Mathematically, this can be expressed as F equals ma, where F is the net force, m is the mass of the object, and a is the acceleration of the object. Newton's third law, the law of action and reaction. Newton's third law states that for every action, there is an equal and opposite reaction. This means that if one object exerts a force on another object, the second object will exert an equal and opposite force back on the first object. These laws are applicable to a wide range of situations, from the motion of planets in space to the behavior of objects in daily life. By understanding and applying these laws, students can analyze and predict the motion of objects and better understand the world around us. In physics, forces are described as either balanced or unbalanced based on their effect on an object's motion. A balanced force is one in which the net force acting on an object is zero, meaning that the object remains at rest or continues to move with a constant velocity. An unbalanced force is one in which the net force acting on an object is not zero, meaning that the object will accelerate in the direction of the net force. Here are some key concepts related to balanced and unbalanced forces. Net force. This is the sum of all the forces acting on an object. If the net force is zero, the forces are balanced and the object remains at rest or moves with a constant velocity. If the net force is not zero, the forces are unbalanced and the object accelerates in the direction of the net force. Force diagrams. A force diagram is a graphical representation of the forces acting on an object. It shows the direction and magnitude of each force acting on the object. Newton's second law. This law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Mathematically, this can be expressed as F equals ma, where F is the net force, m is the mass of the object, and a is its acceleration. Calculating net force. The net force acting on an object can be calculated by adding up all the individual forces acting on the object. If the net force is zero, the forces are balanced, and if the net force is not zero, the forces are unbalanced. For example, if an object has two forces acting on it, one with a magnitude of 5n to the right and the other with a magnitude of 3n to the left, the net force acting on the object is 2n to the right, 5n 3n equals 2n. Understanding the concepts of balanced and unbalanced forces is important in many fields, including mechanics, engineering, and physics. By analyzing and predicting the behavior of objects in motion, scientists and engineers can design and develop new technologies, improve safety standards, and advance our understanding of the world around us. Circular motion is the motion of an object moving in a circular path. This type of motion can be described in terms of velocity and acceleration, as follows. Velocity in circular motion. In circular motion, the velocity of the object is constantly changing, even if its speed remains constant. This is because the direction of the velocity vector is changing as the object moves around the circular path. The velocity vector is always tangent to the circular path, meaning that it is perpendicular to the radius of the circle at any given point. The magnitude of the velocity vector, or the speed of the object, is constant in uniform circular motion. Acceleration in circular motion. The acceleration of an object moving in a circular path is always directed towards the center of the circle, and is called the centripetal acceleration. It is caused by a centripetal force, which is required to keep the object moving in a circular path. By understanding and applying the concepts of velocity and acceleration in circular motion, students can better understand the behavior of objects moving in circular paths, such as planets orbiting the sun, cars turning around a curve, or a ball moving in a circular path. Terminal velocity is the constant maximum velocity that a falling object can reach in a fluid, such as air or water, due to the opposing force of air resistance or fluid drag. As an object falls through a fluid, it experiences a force of air resistance or fluid drag, which opposes its motion and eventually balances out the force of gravity. When these two forces are equal in magnitude, the net force acting on the object becomes zero, and the object falls at a constant maximum velocity known as terminal velocity. Terminal velocity is an important concept in many fields, such as skydiving, aerodynamics, and fluid mechanics. By understanding and applying the principles of terminal velocity, students can better understand the behavior of objects in motion through fluids and predict the maximum speed that they can reach in different scenarios. Moment of force, also known as torque, is a measure of the turning effect of a force around an axis of rotation. It is defined as the product of the force and the perpendicular distance from the axis of rotation to the line of action of the force. Mathematically, it can be expressed as moment of force equals force x perpendicular distance from axis of rotation, or tau equals Fd, where tau is the moment of force or torque, F is the force applied, and d is the perpendicular distance from the axis of rotation to the line of action of the force. The SI unit of torque is the Newton meter, N*m. The principle of moments states that for a body to be in rotational equilibrium, the sum of the clockwise moments around a point must be equal to the sum of the anticlockwise moments around the same point. In other words, the net torque acting on a system must be zero for it to be in equilibrium. Mathematically, this can be expressed as sigma tau underscore clockwise equals sigma tau underscore anticlockwise, where sigma tau is the sum of the torques acting clockwise or anticlockwise around a point. The principle of moments is used in many fields of engineering, such as in the design and analysis of structures, machines, and mechanical systems. By understanding and applying the principles of moment of force and the principle of moments, students can better understand the behavior of objects in rotational motion and predict the effects of forces on rotating systems. The center of gravity is the point at which the weight of an object is concentrated and the object can be balanced perfectly. It is the point where the gravitational force acting on the object can be considered to act through. The center of gravity is dependent on the distribution of mass in an object, and it can be located inside or outside the physical boundaries of the object. The center of gravity plays an important role in determining the stability of an object. An object will be stable if its center of gravity is located directly above its base of support. The base of support is the area on which an object rests or is supported, and it is determined by the contact points between the object and its surroundings. A wider base of support makes an object more stable, as it provides a larger area for the object to rest on and makes it more difficult to tip over. The lower the center of gravity of an object, the more stable it is. This is because a lower center of gravity means that there is a shorter lever arm between the center of gravity and the base of support, which reduces the torque that can cause the object to tip over. For example, a top-heavy object like a tall vase is more likely to tip over than a wider object with a lower center of gravity like a table, even though the table may be heavier overall. This is because the vase has a higher center of gravity and a smaller base of support, making it easier to tip over. Understanding the center of gravity and the factors that affect stability can be important in fields such as engineering, architecture, and physics. By considering the center of gravity and the base of support, engineers and designers can create more stable and safe structures and machines. In physics, a force vector is a mathematical representation of a force that includes both its magnitude and direction. A force vector is typically represented graphically using an arrow, with the length of the arrow representing the magnitude of the force and the direction of the arrow representing the direction of the force. Sign conventions using arrows can be used to distinguish between forces acting in opposite directions. For example, if a force is acting to the right, it can be represented with an arrow pointing to the right, while a force acting to the left can be represented with an arrow pointing to the left. When two forces act in the same direction, they are said to be parallel and their vectors will be in the same direction. When two forces act in opposite directions, they are said to be antiparallel and their vectors will be in opposite directions. Perpendicular vectors are two vectors that are at right angles to each other. The magnitude of the resultant vector of two perpendicular vectors can be calculated using the Pythagorean theorem. If vector A has a magnitude of A and vector B has a magnitude of B, then the magnitude of the resultant vector C can be calculated using the equation C equals square root A superscript 2 plus B superscript 2. The direction of the resultant vector can be calculated using the tangent function as follows. Tan equals op/adj, where theta is the angle between the resultant vector and one of the original vectors, op is the magnitude of the component of the resultant vector perpendicular to that vector, and adj is the magnitude of the component of the resultant vector parallel to that vector. By understanding the properties and calculations of force vectors, students can better analyze and predict the behavior of objects in motion and the effects of forces on those objects.